2 weeks.
2 hours. Give me a second. I have a concussion. Okay?
It's something too.
It's a two of some form of measurements.
2 seconds.
Yeah, the accident, I was coming back from High Prairie that night from reffing hockey.
Yeah.
And so it didn't affect us getting home. But yeah, there was a truck. It didn't plow into the construction zone. It was just where the lane
Yeah.
merged together.
Yeah, until
And it was on its side, and there was a bunch of vehicles at the bottom, and then there was a whole bunch at top too.
That was me.
You're one of them.
I was one. If you look for a blue Malibu, I'd be right there.
Yeah, I was kind of watching the road because it was slippery that
Oh,
night.
wow. Because it was freezing rain that night.
It was
I don't
terrible.
even know. I was driving. I was being stupid. But, you know. We all got there safely.
Okay. So now we're going to see what derivatives are. And you should recognize that formula. The derivative of a function f at a number a is given by, so f prime a means the value of the derivative. That's what that prime means. It means you're taking the derivative of the function. So f prime at a means the value of the derivative when the variable equals a equals the limit as h approaches 0. And you should recognize that formula because that is one of the formulas we use for finding the limit from first principles. So this tells us then that what we were doing when we were finding the slope of the tangent, or we were finding the instantaneous rate of change, we were really finding the derivative of the function. Okay, that's what we were doing, finding the derivative of the function. So we're going to see that you can find the derivative using these formulas for first principles, but then we're going to see an easier way to find the derivative of a function. So you're not going to have to use this formula after we go through that part. Okay? And it is much easier to find the derivative. However, we'll go back and we'll use this formula to find f prime 4. Now notice in this case that the function is not rational, so therefore you don't have any non-permissive value here, right? But we want to find the derivative, so we have to use this formula because it tells us to find f prime 4, which means the value of the function, value of the derivative of the function when the variable x equals 4. So we have to take the derivative, which means we have to use this formula. So that's where we'll start. We'll start by using this formula. So we'll write it as f prime x at first. So it'll be the limit as h approaches 0 of f at a plus h, and I shouldn't, in this case here, the value of a is 4. So it'll be 2 bracket 4 plus, and instead of, well, I guess we'll use the variable h, might as well. We technically could have used the variable x instead because that's the variable in the equation, but it doesn't matter. So the formula says that whatever x is, which in this case is 4 plus h, it's squared minus 5 times 4 plus h plus 6 all over h. So if we multiply out 4 plus h all squared, remember you're squaring the binomial, it's not just 16 plus h squared, that means 4 plus h times 4 plus h. So you could FOIL that out, or we've been using a shortcut for squaring a binomial, which is squaring the first term, multiplying the two terms together and double, squaring the last term, minus 20 minus 5h plus 6 all over h. So if we multiply out those brackets, we're going to get 2h squared plus 16h plus 32 minus 20 minus 5h plus 6 all over h. So I'm going to have the limit as h approaches 0. I've got 2h squared 16h minus 5h is plus 11h. 32 minus 20 is 12, plus 6 is 18. Now I just want to check this because something doesn't look right here. Oh, I'm sorry. I know what I forgot to do. I forgot to subtract f at a. So I just did the f at a plus h part here on the top. I didn't subtract f at a. So I need to go back and fix this, or add that in there, I should say. So minus f at a, which is, it's the value of the function when x equals a, or x equals, in this case, 4. So when I let x equal 4 up here, 4 squared is 16 times 2 is 32. Minus 5 times 4, so minus 20, plus 6. So 32, take away 20 is 12, plus 6 is 18. So that's a minus 18 there that we're going to subtract on here. And then these 18s cancel. So that gets rid of the constant term. And now we can evaluate this by factoring. There's a common factor of h there, which leaves us with 2h plus 11 all over h. And the h's cancel. And now we can evaluate this when h does equal 0, and the answer is just 11. So there's the value of the derivative of the function when x equals 4. It's positive 11. So we've seen that this has several applications, right? If we wanted to find the slope of the tangent to that curve when x equals 4, that would be the slope of the tangent. Okay, so that's one of our applications of the derivative. The tangent line to the curve y equals f at x at point a comma f at a is a line through a comma f at a with a slope of f prime a. Excuse me. So the derivative is one of the applications. It's the slope of the tangent. The other one is the instantaneous rate of change, right? We used that formula before, and we said that that gave us the instantaneous rate of change of y equals f at x with respect to x when x equals a. Also, if f at s equals f at t is the position function of a particle, then v, the velocity, can be found by taking the derivative of a. Okay, so the velocity is the instantaneous, or it gives us the instantaneous velocity at time equals a. So number 2 says find the derivative of f at x at equals x squared minus 3x at any number a. So this is like the general derivative, and use it to find the slopes of the tangents to the parabola y equals x squared minus 3x when x equals 1, when x equals 3, and when x equals 5. So again, we've seen that the derivative, which you can determine using those first principle formulas, gives us the slope of the tangent or the instantaneous rate of change as well. So we can find out what the general derivative is. So you notice the difference between this one and the previous one. The previous one, we wanted to find the value of the derivative at a certain value of x. In this case here, we don't want to use a certain value of x. We're not at first. So we're going to come up with a general derivative. So again, the general derivative can be found by using that limit formula, the limit as h approaches 0. And now the first part is f at a plus h minus f at a all over h. So this will be the limit as h approaches 0. So the first part of this is f at a plus h. So wherever I see the x, I'm going to replace it with a plus h. So it'll be x squared, which becomes a plus h all squared, minus 3x, or 3 times a plus h. The second part is minus f at h or f at a, I should say. So instead of x squared minus 3x, it'll be a squared minus 3a. We need to keep the same variable here. So this will be the limit as h approaches 0. If I square the a plus h, it'll be a squared plus 2ah plus h squared minus 3a minus 3h minus a squared plus 3a. And now we can simplify this. So the first thing you may notice is that a squared minus a squared cancels. We've got a minus 3a plus 3a. They also cancel. So what are we left with? We've got the limit as h approaches 0 of h squared plus 2ah minus 3h all over h. And now all terms have a factor of h in it, so I can divide everything by h, or I could take out a common factor of h and I'd get the same thing in the end. I would cancel the h common factor on top with the h on the bottom, but again, because all four terms have a factor of h in, I can just divide each term by h, and that'll give me h plus 2a minus 3 all over 1, because you divided everything by h. And now because you've gotten rid of that h on the bottom, you can let h equal 0 here, and you just get 2a minus 3. Or in terms of x, 2x minus 3. So there's the derivative. The derivative of x squared minus 3x is 2x minus 3. The general derivative. And we're asked to find the slopes of the tangents at those three different values of x. So f prime 1, the value of the derivative when x equals 1, which again gives us the slope of the tangent at the point where x equals 1, will be 2 take away 3, or negative 1. F prime 3 will be the value of the derivative of x equals 3, which again would tell us the slope of the tangent at the point where x equals 3. So 2 times 3 is 6 minus 3, which is 3. And finally, f prime 5. Two times 5 is 10. Take away 3 is 7. So that would be the slope of the tangent line when at the point where x equals 5. So again, what we've seen that if the equation f at x equals x squared minus 3x, the derivative is 2x minus 3. So now let's do the same thing for the function f at x equals x squared. Find the derivative of that. So again, we can find the derivative f prime x by using this limit formula. The limit as h approaches 0 of f at a plus h minus f at a all over h. And in this case, I'm going to change the variable to x. So instead of wherever I see an h, I'm going to replace it with an x, because that is the variable in the equation. I don't have to. I can do it like I did the previous one, keep the h there to the very end, and then sub the x in after. It doesn't matter. So in this case here, though, I'm just going to change the variable to x. So wherever we see h, we replace it with x. Okay, but the first part will be f at a plus h, or a plus x, which means that the x in the equation is replaced with a plus x. minus f at a, or f at x. I'm sorry, f at a. It's just the h's that are replaced with x. All over x. So this would be the limit as x approaches 0. So when you square a plus x, it's a squared plus 2ax plus x squared minus the a squared all over x. The a squareds will cancel. And now both terms on top as well as the one on the bottom have an x. So we can divide everything by x. And it'll be 2a plus x when x equals 0. I'm just left with 2a or 2x. So the derivative of x squared is 2x. All right, so this next one is going to require a bit more work, a bit more algebra, because the function is a rational function. So we want to find the derivative f prime if f at x equals x plus 1 over 3x minus 2. So again, there's going to be a bit of algebra that we're going to have to do here. So again, f prime x can be found by, the first part is f at a plus h. Oops, I need to put the limit there. So the first part is taking the equation and replacing x with a plus h. So I'm just going to leave the h in there, and then we'll put the x back in after we're done going through all of this. But again, the first part is f at a plus h. So we're going to replace the x with a plus h. The bottom, again, we replace the x with a plus h. Minus f at a, so it'll be a plus 1 over 3a minus 2 all over h. Now, I've got on top here, I've got a rational function that I want to combine with subtraction. So I'm going to do that by getting a common denominator. Okay? So if I want to add or subtract these two together, combine them into one expression, I need a common denominator. And it will be both of these denominators. So I'm going to have to multiply the first one, top and bottom, by 3a minus 2. So I've got the limit as h approaches 0. So I've got a plus h plus 1. That needs to be multiplied by 3a minus 2. Minus the second term. I'm missing the denominator there of 3 bracket a plus h, take away 2. Which if I multiply that out, it'll be 3a plus 3h minus 2. All over, again, 3a plus 3h minus 2, bracket 3a minus 2, and that is all over h. Now before, when we did these limits, we did things a little bit different. You might remember that we multiplied all the terms by the least common denominator, all of the terms, the two terms on top, the one on the bottom. We did it that way. Well, we're doing it slightly different this way, but the first way would work as well. Okay, the first way would work as well, but we're going to see that this is going to work also. So here we go. So we got to multiply all this out. It's the limit as h approaches 0. So on top, using this derivative property, all three terms in the first bracket are multiplied by the 3a and then by the minus 2. So first multiplying all three terms by the 3a. That'll give me 3a squared plus 3ah plus 3a. Then everything by negative 2. Negative 2a, negative 2h, negative 2 minus. Now I'm going to multiply everything out in those last two brackets. First multiplying everything in the trinomial here by the a in front. So it'll be 3a squared plus 3ah minus 2a. And then everything by the plus 1. It'll be positive 3a, positive 3h, and minus 2. So that is all over our common denominator, which is 3a plus 3h minus 2, bracket, 3a minus 2. And then instead of dividing by h over 1, we can multiply by the reciprocal. We can times by 1 over h. Instead of dividing by h, which we can write as a rational expression, h over 1, we can multiply by the reciprocal. We can multiply by 1 over h. I'm just going to snip this to a new page here. Oh, because I kind of ran out of room. All right. This minus sign in front of the bracket here changes all the signs inside. So this positive 3a squared will cancel with the minus 3a squared. This positive 3ah will cancel with the minus 3ah. If you remove the brackets, all those signs in the second bracket are going to change. Okay. This positive 3a will cancel with this. That will become a minus 3a. This negative 2a we cancel with this one because it's going to become a positive 2a. And this minus 2 is going to cancel with this minus 2 in the brackets because when we remove it, it'll become a positive 2. So we see that almost all of those terms cancel. Almost all of them. If we write out what we have left, we have the limit as h approaches 0. So all we have left on top is negative 2h, and this will become a negative 3h. That becomes negative 5h. All over 3a plus 3h minus 2, bracket, 3a minus 2. Don't forget this is all multiplied by 1 over h. And that h on the bottom will cancel with the h after the negative 5. So we are left with the limit as h approaches 0 of just negative 5 over 3a plus 3h minus 2, bracket, 3a minus 2. And we can now let h equal 0. We can evaluate this limit. So all that's going to happen is that this middle term in the first bracket is going to disappear. When you let h equal 0 there, it's going to be 3 times 0, which is just 0. but you're still left with 3a minus 2, which is the second factor on the bottom. So when we evaluate this limit, it'll be negative 5 over 3a minus 2 all squared. And then if we write it in terms of x, it'll be negative 5 over 3x minus 2 all squared. There's the value of the derivative of that original rational function. So a lot of algebra there. And we're going to see as we start going through this course, there's going to be times when it's going to be pretty heavy in algebra. But it's nothing that you haven't done before. It's maybe a little more complicated than you're used to doing, but we're following the same rules that we always have. Okay? So there's the value of that derivative. So looking at number 5, if f at x is that radical function, the root of x plus 2, we want to determine f prime x. And again, we can do that using this limit formula. F prime x can be found by taking the limit as h approaches 0. And in this case, I'm going to replace the, well, let's write out the equation we're using once again. But I'm going to replace the a with the x right at the start. So instead of a, wherever I see a, I'm going to replace it with x. So the first part is f at x plus h. So it'll be the root of x plus h plus 2 minus f at x minus the root of x plus 2 all over h. And I forgot to write the limit in there, so let's do that. So we've seen ones like this before. We've seen ones like this before, and what we've done is we have multiplied top and bottom by the conjugate, right? We've multiplied top and bottom by the conjugate. So I would multiply here. Actually, let's write it out on the bottom. I've got room. This will be the limit as h approaches 0 of the root of x plus h plus 2 minus the root of x plus 2. And I'm going to multiply by the conjugate, which will be the root of x plus h plus 2 plus the root of x plus 2. So multiplying top and bottom by that conjugate. So when you multiply those out on top, when you FOIL them, the root of x plus h plus 2 times the root of x plus h plus 2 just gives us x plus h plus 2. The outer and inner products cancel, always do. So you're just left with the two last terms multiplied together. A negative times a positive is a negative. And the root of x plus 2 times the root of x plus 2 is x plus 2. And again, I put that x plus 2 on top in brackets because you have to subtract all of it. And the minus sign in front changes all the signs inside, so both the x's and the 2's cancel. You're just going to be left with h on top, which will then cancel with the factor of h on the bottom. Right? The h's will cancel. Yeah. Yep.
Why is zeros in the gray and one are you cancel out and get one so it unifies with the zero?
Say that again.
Like when we divide h by h, we get one, right?
They cancel, so you don't have an h there anymore, so you're not dividing by 0. The factor of h is gone, so you're no longer dividing by 0.
What if h is invisible if zero?
Pardon me?
H is invisible if there's zero.
You're going to put a 0 in wherever you see h, correct?
So when you factor out zero from zero, which is
No, you're not factoring out 0. You're factoring out the h so you can cancel it. That's the whole point of doing it. The h disappears when you divide top and bottom by h. They're gone. And so we no longer have a factor of h anywhere on the bottom. Actually, on top either now, but that's not always going to be the case. But you got to get rid of the h on the bottom, the factor of h. As it stands right now, I've gotten rid of that factor of h on the bottom, so I can let h equal 0.
yeah, like I know that's how it works, but why is it like that, right? Like why can you cancel it out when it's a variable?
Well, I guess you could say that you're canceling out in number form because you'd have a 0 on top and a 0 on the bottom. If you divide something by itself, technically you get 1. So it's the same thing. Even though if you try it in your calculator, I don't think you'll get 1, because as soon as you tell your calculator to divide by 0, it's going to spit out an error every time. So that's why you leave it as a variable, so that you can cancel them. But as soon as you put the 0 in there, if you do it in your calculator, you're going to get an error every time. Even though you know when you divide something by itself, technically you get 1. But your calculator wouldn't look at it that way. Pretty sure. 0 divided by 0. Yeah, doesn't look at it that way. Okay, but we have gotten rid of the factor of h on the bottom. So if we write out what we have left, so we no longer need those brackets there because we've gotten rid of the factor. And when we do let h equal 0, it'll just be 1 over. You're going to have the root of x plus 2 plus another root of x plus 2. So it's going to be 2 root x plus 2. So there's the derivative. So again, lots of algebra there. Now, we are going to be learning very soon here how to find these derivatives without using these first principle formulas. And we're going to see for those first couple ones where it's just a polynomial function, it's very, very fast, very simple. You don't have to use these formulas. We'll show you the simple way to find the derivative of expressions like that, polynomial functions. But we're also going to learn there's going to be some different rules. How do you find the derivative of a polynomial all raised to a power? We're going to see there's a special rule to differentiate that. We're also going to find out that there's going to be special rules to differentiate a product where you have one function times another function. Instead of multiplying it out, you can go straight to differentiation. We're also going to find a rule that we can use to find the derivative of a quotient where you have one expression divided by another, okay? Which we saw one like that today already. That was that number 4. That's a quotient, okay? So we're going to find a rule that we can use to differentiate an expression like that without using this first principle formula. And this last one we did, we can write that as a power, x plus 2 all to the power 1/2. So we're going to learn a rule that we can use to differentiate something like that without using this formula. As well, for these ones like x squared minus 3x and y equals x squared, we're going to learn how to do that, and it'll take a matter of seconds instead of using this general formula. Okay, but we'll start looking at that next class. Other notations for derivative. Okay, so we've seen f prime x means an expression for the derivative of f at x. So another common notation that's used is dy by dx. When you see dy by dx, that means the derivative of y with respect to x. That's another notation for derivative. But remember, sometimes our formulas may not involve x and y, right? If it's y equals a function of x, it's dy by dx. But you can have s equals a function of t, and we saw that with position functions before. So then it would be the derivative of s with respect to t, ds by dt. Sometimes just d by dx is used. That represents derivative. Or d sub xy also represents the derivative. Now, we know that the derivative now can be used to find the slope of the tangent, right? So the graph of a derivative can be sketched from the graph of f at x, because again, the derivative of any point is equal to the slope of the tangent at that point. So we can estimate the slopes of the tangents at various points on the curve, and they can be plotted to graph the derivative f prime x. Remember, the derivative is the slope of the tangent. I'm going to look at 3 key points here to start, and those being the local maximum and minimum points. So I've got 2 maximum points. This first one is actually an absolute maximum. It's the highest point on the graph. The one to the right of it is a local maximum. But you see, the tangent lines at those 2 points will actually be horizontal lines. So the tangent line would look like that and like that, horizontal lines. Same as this local minimum down there, the tangent line will be a horizontal line. And a horizontal line has a slope of 0. And remember, the derivative tells you the slope of the tangent. So at these 3 points on the graph of the original function, the derivative will equal 0, because the derivative is equivalent to the slope of the tangent. Okay, so let's plot those points. Change my color here. So wherever that tangent point is, the derivative will be 0, because the derivative is the slope of the tangent. And these 3 spots, the tangent line is horizontal, its slope is 0. So wherever we see those 3 points, the x values won't change. The y values will be defined as the slope of the tangent. And at these points, the tangent line is horizontal, the slope is 0. So this is going to give us our x-intercepts of the graph of the derivative. Now, we cannot determine any other tangent, slope of the tangent on this graph just by looking at it like we just did. However, in this first interval, so the first interval is going from negative infinity to this tangent line, or this x-intercept. Anywhere in that first interval, because the graph is rising, the tangent line will have a positive slope. The tangent line will have a positive slope. So the value of the tangent will be positive, which means that the graph of the derivative will be positive in that interval, or it'll be positive values of y, or above the x-axis. So in this first interval, from negative infinity to this tangent point, or this x-intercept, when we're graphing the derivative graph will be above the x-axis. It has to be positive because the tangent lines will all be positive. Then in this next interval, so if I number these 1, 2, and 3, our 3 min and max points, which correspond to our 3 x-intercepts for the derivative, between point 1 and point 2, the original graph is decreasing in value, which means that the tangent lines will have a negative slope there, which means the value of the derivative will be negative in this interval. It'll be below the x-axis. The values of y will be negative. Then, from point 2 to point 3, the original graph is increasing. The tangent lines will have a positive slope. So the values of the derivative will be positive. The values of y will be positive. This graph will be positive above the x-axis. And then from point 3 down to positive infinity, as we go to the right, the graph will be decreasing forever. So the tangent lines will have a negative slope. So the value of the derivative will be negative below the x-axis down here. So we know that the derivative will be positive in the first interval, okay? And then when it gets to point 1, the derivative goes to negative, which means the graph is going to come down. It's going to cross the x-axis. And then it's going to go up to the next x-intercept. And in this next interval, we've said that the derivative will be positive, or the graph will be above the x-axis. And then it'll go down to the last x-intercept. And from there, it'll go downwards forever because the graph is negative below the x-axis. We don't know exactly where this minimum point is. We don't know exactly where this maximum point is. But that doesn't matter. It's just a sketch. But we do know where the x-intercepts of the derivative are, and we also know where the graph of the derivative is above as well as below the x-axis. It's just a sketch. But there would be a sketch of the derivative of that function. Okay? So, when we use those formulas before to find the limit from first principles, now we're seeing we were really finding the derivative. And so you can find the derivative using those formulas from first principles. But moving forward, starting tomorrow, we will learn how we can find the derivative without using those limit formulas. And again, we're going to see for just a straight polynomial function, no matter what the degree is, you're going to be able to do it in a matter of seconds. Okay? And then we'll learn rules of how you differentiate a product, how you differentiate a quotient, and also how you differentiate some expression raised to a power. So we'll learn all those rules as we go through. Sometimes there's still going to be a bit of algebra involved, right? But it's not going to be rocket science. Take it to Mr. Bird. Okay. You can work on page 75 to 76. Questions 2, 4 through 7, and then 8 questions A through C. Yes, sir. Pardon? Nope. Tomorrow, right, Josh? Tomorrow.